So this project I want you to do is make a spreadsheet that will calculate the Carnot cycle, the state variables table, the thermodynamic values, heat for each leg, the engine output, meaning, how many kilojoules it puts out, how much heat goes in, and what's the efficiency calculated both ways. So this will be a project that I want everybody to do, because in doing this, you're going to learn all of the equations and learn how to put it all together. Now, there is one section here that I have that's a little fancy. You don't have to necessarily do it this way, but I have like a ratio of atomic, linear, and nonlinear molecules in there, all adding up to 100. So I've got here 100% atomic, so monatomic gas, but if I wanted to do 100% linear, then I would just change the top one to 0, the next one to 100, and then it would calculate the third one. It would take 100 minus the sum of the earlier two. So you change two of them, the third one will update automatically so that they always add up to 100. But again, you can do that however you want. Then I calculate the CV for each of those, because we know the CV for an atomic gas, we know the CV for a linear or a nonlinear gas, and then we can calculate CP and we can get gamma. So whatever mixture of gas you have, it's just the weighted average of all of those CVs and those CPs, and you get gamma. So then you can calculate your adiabatic relationships. Without gamma, you can't really calculate those. So that's what you need for that. This is the one cell that really bothered people in the past trying to figure this out. This maximum temperature from the adiabatic temperature volume relationship, the adiabats have to connect the two isotherms, okay? And so if we go too high in temperature, this adiabat doesn't reach that isotherm at the appropriate volume, and so it just prevents you from making a cycle that doesn't connect. Okay, so I just took the maximum pressure and then the minimum volume, maximum volume, and there's a maximum temperature that you can get these isotherms apart from each other before you end up with something like a 200% efficiency or something like that. It doesn't make sense. And so I put in some if-then statements in there. There's a video on either YouTube or Blackboard. I'll make sure that it's clear on Blackboard where to go for that video, where I walk through all of these cells. Okay. But anyway, this is the project. Now this is going to be worth, I don't know, I think it's like 15 points on your exam. So it's not just a homework, which your homeworks are 10 points each week. And so that's divided over like 150 points, for the whole semester. So each individual week's homework isn't worth very much, but 15 points on an exam is a whole letter grade and then some. So do well on this. I'll grade them. I want to go in and I want to be able to change the cells and see that the efficiency works out and all of that stuff. I want to be able to see the plots. Now this has a plot. Let's see, let me pull up the spreadsheet. Yeah, because it's this week and it'll teach you a lot. So let's go ahead and make it due like Thursday night before the exam. Okay, and let me swap this over, this window capture. Excel, here we go. All right, there you go. So looking at this Excel file, yeah, you can see my mouse. Okay, so I have the graph here. It's going off scale a little bit. So let me change the scale here. Let's go to 6 maybe. Okay. All right, so there's our Carnot cycle. And notice how these, you can't see it? Okay.
I'm looking on the Blackboard right now. It says it's extra credit. Is it actually extra credit?
No, I want to make it.
Okay.
I want to make it 15 points on your exam. Okay. What that'll do is that'll save me from having to wear you guys out on Friday and not be able to finish the exam. So I will have something like this, the spreadsheet shown with some missing points. So it'll be kind of like last time. You'll have some missing points that you need to calculate. So you need to be able to drop in anywhere in the state variables table and calculate it. Maybe this leg here is missing the work value. So you need to know on an isothermal expansion how to calculate the work. And that's an equation on one of your note cards. And then the efficiency, I mean, have the temperature efficiency, but you got to calculate the work efficiency and show your work. Okay, so that's just a check to make sure that you're familiar with the problem and you can drop in anywhere and do it. Okay. But then creating the spreadsheet tool is really handy because then you'll be able to type in the parameters of any engine, the temperatures of any engine, see how they perform and so on. And then you'll have that tool going forward if you ever need to look at it or if you get curious again. Okay, so let me try to, if I use Excel and I can't draw on the screen, so let me snap a picture of this. Okay. We'll go over to the PowerPoint. Yeah, here, we'll just use this one. Okay. Okay, so looking at this, when you're trying to make your plot here in Excel, good grief. Okay. Okay, so when you're trying to make your plot in Excel, it can be pretty tricky. You're going to have 4 columns of data. You're going to have the column that is this isotherm. And maybe this one will be column 2 here. And this one down here, this isothermal compression might be column 3. And then this adiabat here might be column 4. And then if you plot these, it gets confusing if this isotherm goes past this adiabat. And so one way to do it is for the expansions. Notice this adiabat right here is higher than this isotherm if I were to plot them on this plot. And so for these 2 columns, column 1 and 2, I take the minimum of those 2 columns. So I'm actually plotting a line right here that's the minimum of column 1 and 2, and then when it hits here, I'm still plotting the minimum of column 1 and 2 because the isotherm goes above the adiabat. So that's the trick for getting this to plot out. I have in these 2 columns, column 1 and column 2, I do min and I plot the expansion because that's the minimum of those 2 columns. And then going back here, this adiabat is below the isotherm, and so I'm going to do max column 3 and column 4. And so then that will plot this return trip up here. And then I can just take for the points A, B, C, and D, those can be plotted from the state variables table. Just markers only, and you'll get all 4 of those points, the PV points in the state variables table. If you plot those, then you'll get the markers. Okay, and that's described in the video on the spreadsheet tool. But this is a little tricky chart because you got 4 columns. If you plot all 4 columns on there, it's going to be very confusing. Now this particular Carnot cycle is not that confusing, but this one here is because when you get to this, look how gradual the slopes are here for D. So for, this would be, say, this was column 3, and this was column 4. And right here, these two lines almost have the same slope, and so they're just very close to each other, and it's very hard to see that transition. And so when you have both of those columns plotted past each other, it's very, very difficult to see. So it's better to do this filter. We're just taking the maximum value for columns 3 and 4, the minimum values for columns 1 and 2, and plotting that, and you get this nice shape that's easy to see and easy to understand. Okay, so that's the trick for plotting this. Okay, so now let's do our calculations. So for the isothermal expansion, get your numbers out and start calculating the amount of work that was done for the isothermal expansion. So this is going from A to B, so we have VB over VA. Okay. 0.589. Now this is going to be, which R do we use here? So we've got moles here, we've got Kelvin here, we want joules. So that's the units we need, 8.3, the joules per mole Kelvin. So we use 8.3 for that. T hot was 922. That was for everybody. Did y'all end up with 5.89 moles as well in yours? So go ahead and use your number of moles. We want you to use your values. Okay. And then VB for me was 0.718 liters. A was 0.31. So looking at this, I've got a fraction that's greater than 1, so my natural log is positive, and I have a minus sign up front to show that the work is being done on the surroundings, and it's negative 3.79 kilojoules. That's what I get from mine. You guys are going to get whatever you get. Okay. Q equals minus W, which is equal to plus 3.79 kilojoules. So whatever you end up with, it's just change the sign, that's how much work. And on the isothermal expansions and compressions, that's the way it works. Because we're putting in heat to keep the temperature the same on an isothermal expansion. Golly. It's this touch thing. I touch it and it changes the slide, and it didn't used to do that. Okay, so the work for the adiabatic expansion, okay, it's the number of moles, and there's no negative sign or anything, so it's 0.589 moles times CV. We're doing a monatomic gas. Okay, so CV is 3/2 R. And then here's, we got to pay attention. It's T cold minus T hot, because that's the other end of the adiabat. We're going down in temperature. So its final is T cold, initial is T hot. So our T cold in this case was 372. Two was our T hot. It's a negative number, so we're going to get a negative work, which is what we want. 8.314 times 2.589 times. So negative 4 kilojoules. And what is Q for this one? You can look up there and see it, but I mean, it's 0. This is an adiabatic expansion, so we're not putting heat into the system, we're not taking heat out. And one way to think of that is it's happening so fast, there's really no time for appreciable heat to be exchanged. So by definition, heat is 0. Okay, now let's look at the compression. I mean, if you have questions, always just stop me. Everything's going straightforward here. So then the compression, we can see how much less heat it takes, or how much less work it takes to compress the gas at the lower temperature. Because we're resetting the system now. We're compressing the gas and going back uphill. But we're able to do that spontaneously because of the inertia of the system. You remember the Stirling cycle had a little flywheel on it? That little flywheel stores some of the energy so it can compress the gas on the next cycle. And the reason it's able to compress the gas is because it's at a colder temperature. So if we didn't have a drop in temperature with that adiabat, the engine would stop. Yeah. Okay. Okay, so then our final volume is the volume at spot D. So that's going to be 1.2 liters. And VC is 2.8. This is a fraction is less than 1, so this is going to be negative. And that's going to cancel the negative sign out front, so this is going to be a positive work value, which is what we want. 1.2, 2.8. Two times 8.314 times 1.589 times HA sign. So positive 1.54. This is an isothermal expansion, and so that's equal to minus work. So Q would be negative 1.54 kilojoules. Now look at this equation here. For dA, this adiabat, it has the same delta T but different sign, right? Same CV, same number of moles. So this is just equal to the opposite sign of work BC. So that'll save you a little bit of time. This is positive 4.04 kilojoules. and QDA is equal to 0 by definition. So the only positive, so look at Q here. Q is negative here, so that means heat came out of the system. Q is 0 here, and Q is 0 here. And Q is what we spent money on, right? That's our fuel. So the only fuel here, the only cost, the only heat in is this positive 3.79. And so that's QAB, that's the heat in for our engine. So we can calculate our efficiency. 3.79 kilojoules on bottom. And then the sum of all of our work values, we can add that up. So let's add that up. We have 7, 0.54 and 4.04. So I end up with 2.25. Negative 2.25 kilojoules. But I take the absolute value to get rid of the negative sign because we don't want to have negative efficiencies. That's what we're calculating here. 3.79. So it equals 59.4%. 59.4%. So that's unbelievably good. And I don't know that our Toyota engine or Nissan or whatever one we're calculating actually runs at that. So most of your gasoline engines max out around 25%. So diesel engines get a little bit higher heat and can get up to 35%. So where could we be wrong in our problem here? We kind of treated a gasoline engine as a Carnot cycle. It's really not a Carnot cycle. That could be the source of our error, but where's the main place where we had to make some assumptions that we really didn't know if they would hold in a real engine? So we can go back to our state variables table, state variables table. Let's see if we see what we had before that. Yeah, here we go. Here's some of our baseline data. We looked at the maximum pressure. We kind of got that off of automobile sites, so I feel pretty good with the maximum pressure. This would be saying our engine's running at that maximum pressure. Okay, maybe it's not. But what number on here are we least confident in, I guess is what I'm saying. Are we least confident in the displacement? No, we got that right off the spec sheet for the motor. What about the compression ratio? Also a pretty good number. I got the 2100 PSI from automobile sites. Is there a number on here that's weaker than any of the others, is I guess what I'm trying to say. Because I don't think we're going to get 59% efficient wheel engine. Which one? Well, we have two choices, T hot or T cold. Yeah. I kind of hinted at it when we were talking about it. Yeah, so the 210 is the radiator, like the cooling system. That's what you see on your dash. It's around 210. And this is saying that that's the lower isotherm temperature inside the combustion cylinder. I mean, the hot temperature could also be off, but But think about what the low temperature is. The low temperature is how cold the gas is when we compress it. And so it's not fair to say it's the exhaust gas, really, because it's still coming out hot. But the temperature the gas going in is going through the engine parts and so on. The engine's hot. Maybe the metal parts are higher than 210, but you know, it may be that the hot gas isn't cooling down. Maybe that last 80 baths not coming all the way down to 210. So we have it's probably the heat of the exhaust gas after we push the cylinder all the way down. It's not getting all the way back down to that cold isotherm. And so it's probably the low temperature that's too low. Because again, one way to calculate the efficiency is to, let's see, efficiency for the Carnot cycle is equal to 1 minus T cold over T hot. So if this is equal to 0.25 equals 1 minus T cold over 1200, let's see, what do we say? There's 972, right? 972 Kelvin. Then what is TC? Okay. So 1 minus that is equal to 0.25. Okay. So this thing is equal to 0.75, right? So yeah, 1 minus 0.75 is 0.25. So this whole piece, we can scratch this out. This is equal to 0.75. And so TC would be 75% of 972. What is that temperature? 972.
So 29.
Yeah, 729. Yeah. So this is saying that our T cold might be 729 Kelvin, much higher than 210 if our engine was running at 25% efficient. So again, the separation of these two temperatures, that's the efficiency of your engine. The farther apart those temperatures are, the more efficient the engine. So if we were to try to get to 100% efficient, we'd have to have, you know, like an infinite high temperature, which means this denominator would be infinity. So it'd be essentially 1 minus 0, or this would be 0 Kelvin, 1 minus 0. So we either cool the cold side down to 0 Kelvin or raise the hot side up to infinity. Either way, we're getting closer to perfect efficiency. But you can see how unattainable those are. If you put 0 Kelvin cold reservoir in contact with anything, you're not going to be able to maintain it at 0 Kelvin. So there's just no way to get a perfectly efficient engine. But driving the hot and cold temperatures apart, those isotherms, that's the way you get more efficient engines. So you need to have hotter materials that can withstand hotter temperatures. You have to harvest as much heat out of the gas as possible so it leaves as cold as possible. So before that exhaust valve opens, we want the gas to be as cold as possible. That means we've pushed the piston as far as we can push it, and the gas has lost its kinetic energy, so therefore it's colder, and that's how these heat engines work.